A pleasant day to you. Let me present to you a simulation of a circuit with a MOSFET amplifier. By the way, I am Project-RETUYA. I am from the section of B18 under the course of ECEA101L. Now let's proceed to the circuit design. Let's go to the LT Spice program so that I can properly describe the components of the circuit. Okay, so this is the MOSFET amplifier placed in the heart of the circuit. So we can observe that there are two voltage sources. So the first voltage source has an input of a sine V offset where we have DC offset of 0, an amplitude of 1, and a frequency of 1K. We also have two capacitors for the circuit where both of the circuits have the value of 0.12 microfarad. For the first two resistors, for R1 we have an input of 200k ohms, and for the R2 it has a 100k ohms resistance. We also have the RD, RS, and RL. For RD we have 470 ohms, RS has 150 ohms, and RL has an input resistance of 10k ohms. So our MOSFET is BSC035 and 04L. So we have also grounds here. This will be our V in and this will be our V out. So I used for the simulation the DATTRAN 0.005 for running the circuit and getting our parameters and such values. Now we move to the description of the circuit. This is a basic enhancement mode common source MOSFET amplifier design that employs a single supply at the drain and a voltage divider to create the needed gate voltage VG. We know that no current flows through the gate terminal of a MOSFET. Therefore, we can make the following basic assumptions regarding the MOSFET amplifier's DC working conditions based on that information. We also have this formula. V sub dd is equals to I sub d R sub d plus V sub ds plus I sub d R sub s, which will be equal to I sub d quantity R sub d plus R sub s plus V sub ds. Therefore, we have R sub d plus R sub s equal to V sub dd minus V sub ds over I sub d. Now we move along to our measured parameters. The peak power consumed by the MOSFET is equals to 90 milliwatts, where our voltage gain is AV equal to 2.84 over 1, and we have 2.84 V over V. Now, after this, I will show you the frequency response plot, but in the meantime, our bandwidth is equal to 2.78 mHz. Now, this is our frequency response plot, and may I go back to our circuit, so I will show you the other waveforms by clicking the run. Now we will get the input and output waveform, the transient response. So I will click here the V, VO, and V in. So this will be our waveform for the input and output. We can see and what we can observe from these waveforms is that V in has a smaller waveform than that of VVO. And VVO has its peak at almost 3 volts or beyond 3 volts. Now we move now to the waveform of getting our power measurement. We click again the run, and I have here this one. I will just copy it to get our power measurement. It is V quantity N002, comma, capital N004 multiplied to ID quantity M1 plus V quantity N003, comma, N004 multiplied to IG quantity M1. And this is our waveform for the power measurement. So it's very clear now how we got those parameters as shown before. Now, as we can also observe from our circuit, I used these measure commands to get other values from our circuit. And to get those, we will just simply uh, click run and view the spice error log. So for our V in, we have 1.99. For our V out, we have 5.89. For our AV, we have 2.94, which is V out over V in. For our T1, we got 0. For T2, 0.001. For our F in, we got 999.998. For our TO1 is equal to 1.13 multiplied to 10 raised to negative 7. Now for our TO2, we got 0.00098. And lastly, our F out is equals to 1 over TO2 minus TO1, which is therefore equal to 1013.06. So that is our MOSFET circuit, and I hope you have learned something about my simulation. That would be all, and thank you.